For the next few weeks, we're going to be talking about problems that make the assumption of constant acceleration. That means that the acceleration is a number and it doesn't change. The acceleration neither increases nor decreases. Maybe it's 0, maybe it's 4, maybe it's 9.8 meters per second squared. That's the acceleration due to gravity, and we'll talk a lot more about that next time we meet. But constant acceleration just means that the acceleration does not change. It stays the same. So let's jump right in. First thing we can talk about is that when there is a constant acceleration, well, let me back up. We automatically know just from prior experience that average velocity equals delta x over delta t, right? Change in position over the change in time. We talked about that last time. Okay? When the acceleration is constant, we can also talk about average velocity this way. Average velocity can also be initial velocity plus final velocity divided by 2. You can actually just average the initial and final velocity and divide by 2 when the acceleration is constant. You cannot do that if you have a variable acceleration, only when you have a constant acceleration. So this is a new definition for average velocity that only works when we have constant acceleration. Well, let's see what happens when we set those two things equal to each other. So they're both average acceleration. So we can say the change in position, change in displacement over the change in time equals vi plus vf divided by 2. Interesting. So if we wanted to solve for the change in displacement, which would be how far we moved, we could multiply both sides of this by delta t, right? Multiply this by delta t, multiply this by delta t, cancels here, so we would get delta x equals, I'm going to clean this up some, 1/2 vi plus vf times delta t. So now we have an equation where, given constant acceleration, we can find displacement from initial velocity, final velocity, and time. We can also rearrange this equation and solve for time. We could rearrange it and solve for initial velocity. We could rearrange and solve it for final velocity. So let's do a couple quick examples of this with this equation. So let's work this problem. The problem says a racing car reaches a speed of 42 meters per second. If, I should say it, and I can't type, it, let's just ignore that. It then begins a uniform negative acceleration using its parachute and braking system and comes to rest 5.5 seconds later. Find the distance that the car travels during braking. Now, I already told you that we're going to be using the formula we just talked about, which was this, delta x equals 1/2 vi plus vf times delta t. Okay? So we need to figure out what we know already. Well, what are our knowns? So we'll put the knowns in green. And we'll try to stick to that, just so you'll know what you're looking at. Well, I have a velocity. Is this an initial or a final velocity? Well, we're not sure. Is this at the beginning or at the end of the acceleration? Well, it says it slowed down. So we started at 42 meters per second. So that's going to be our initial velocity. 42 meters per second. Okay. What else do we have? I see 5.5 seconds. That sounds like a delta t to me. So we have delta t, which is 5.5 seconds. What are we being asked for? It says find the distance. Distance the car travels while braking. That sounds like delta x. That sounds like displacement, and we don't know it. That's what we're going to look for. Well, okay. We're almost there, but we're missing something. What are we missing? We're missing final velocity. So we need to know the final velocity. Well, what happened in this situation? It says it begins at negative uniform acceleration using its parachute and braking system and comes to rest. Comes to rest. What does that mean? That means it stops. How fast are you moving when you have stopped? 0 meters per second. So we have all our knowns. We know what our unknown is. So we can plug in. Great. So delta x, which is what we're looking for, equals 1/2 times vi, which is 42 meters per second, plus vf, which is 0 meters per second, times the change in time, which is 5.5 seconds. Let's do some arithmetic here. 1/2 42 meters per second plus 0 meters per second is just 42 meters per second times 5.5 seconds. Alright. 42 times 5.5 is... oh, I should be able to do that in my head. Oh well. 1/2 times 42 times 5.5 ends up being 120. Meters per second times seconds. I'll do a side problem over here in blue. We've got meters per second times seconds. The seconds cancel, so we end up, because that's on the top of a fraction, it's on the bottom of one, they cancel, so we end up with 120 meters as our distance. 120 meters. And distance is supposed to be in meters, so we know we didn't screw anything up. That's how you do this kind of question. Let's do another. Okay, here's another one. It says a car enters the freeway with a speed of 6.4 meters per second and accelerates uniformly for 3.2 kilometers in 3.5 minutes. How fast in meters per second is the car moving after this time? Now we got a few things going on here. So let's start by writing our knowns. Again, we'll put our knowns in green. Well, what do we know? We know enters the freeway with a speed of 6.4 meters per second. That sounds like an initial velocity. That's what we started with. 6.4 meters per second. Alright, accelerates uniformly for 3.2 kilometers. That sounds like a displacement. 3.2 kilometers. In 3.5 minutes. That sounds like a time. That's pretty straightforward. How fast in meters per second is the car moving after this time? Well, after a time, that would be a final velocity that we're looking for, and we don't know it. Okay? Alright, great. Sounds like we can just plug in. So, delta x equals 1/2 vi plus vf times delta t. Alright, we're looking for vf, so let's solve this equation for vf. So we got to get vf by itself. That means we got to get everything that's not vf away from that side of the equation. Alright, I'm going to switch to yellow to do this work. So I'm going to divide both sides by delta t. Divide by delta t. Delta t cancels, so we end up with delta x over delta t equals 1/2 times vi plus vf. Okay. Now you get rid of that half, so I'm going to multiply both sides by 2 times 2. So I end up with 2 delta x over delta t equals 1/2. Oop, nope, we got rid of 1/2. That's what we just did. So it just equals, so those cancel, vi plus vf. Okay, so now that means that we can subtract vi from both sides. That's vi. And get vf, I'm just going to flip the equation over, vf equals 2 delta x over delta t minus vi. So that's the formula we actually want to use. I'm going to clean this up. Much better. So now we just plug in. Great. Let's do it. So VF, which is what we're looking for, equals 2 times delta x. Delta x was 3.2 kilometers. Uh-oh. We can't have kilometers. We need to be in meters per second. We need all of our units to agree. So we've got to convert 3.2 kilometers to meters. Luckily, that's easy. We know that that's just 3,200 meters. Okay, crisis averted. 2 times 3,200 meters divided by time, delta t, is 3.5 minutes. Oh, but we need that to be in seconds. So we got to convert, but that's pretty easy. We know that there are 60 seconds in a minute, so we can break out the calculator and take our 3.5 minutes, multiply it by 60 seconds. And if you need to do a conversion factor, great, but I assume all know there are 60 seconds in a minute, and we get 210 seconds. Okay. Crisis averted, chapter 2. Divided by 210 seconds. Minus your initial velocity, which was 6.4 meters per second. Notice that when we divide this distance by this time, meters per second, we'll end up with meters per second minus meters per second, so that it stays the same. So we actually get a velocity at the end that's going to be in meters per second. So let's crunch these numbers. 3,200 times 2 divided by 210 minus 6.4. So we end up with about in the neighborhood of 24 meters per second. And there's our answer. And I hope I didn't make a mistake. I'm sure you'll let me know about it if I did. Okay? But it's really important, especially at first when you're working these problems, to write down your knowns real clearly somewhere. And I really recommend that you do the algebra first when you have to rearrange an equation, because if you plug those numbers in first, it's so easy to forget a sign, or to forget a 2, or to have an extra 2, or something like that. So I really recommend that you rearrange these formulas first before you start plugging in. Okay, let's move on. All right, let's now consider the acceleration equation, which said that acceleration equals change in velocity over the change in time. Well, and we know that change in velocity is really Vf minus Vi over t. So we can compress this and write A acceleration equals Vf minus Vi divided by delta t. We'll keep it as delta t, just because that's what we've done so far. All right. If we multiply both sides of this equation by delta t, cancels over here, we can end up with A delta t equals Vf minus Vi. And we can solve this for Vf by adding actually Vi to both sides. It cancels over here. So we can get another new equation. Vf equals Vi plus At. Final velocity equals initial velocity plus acceleration times time. And I keep forgetting to make this delta t. Do this way. There we go. Okay, there's another new equation for Vf, Vi, A, and delta t. And we'll use it in just a moment, so make sure you write it down. And really, it's not hard to arrive at. You should be able to derive this if you absolutely needed to. So let's do another. For this one, we need to start with our previously two derived equations. So we're going to start with the one we just did, which was Vf equals Vi plus A delta t. And we're also going to use delta x equals 1/2 times Vf plus Vi times delta t. All right. we're going to do here is this. We're going to substitute this into here for VF because, well, VF equals that, so we can do it. So this is what it's going to look like. We're going to have delta x equals 1/2 times, instead of VF, we're going to write VI plus A delta T. So that's just this part. We still have to add VI plus another VI, the one that was already there. This one got plugged in. This one was still left, times delta T. Oh, that's ugly. Well, let's see what we can do. So we get delta x equals 1/2 times, let's see, I get VI plus VI. That's VI plus VI is 2VI plus A delta T times delta T. Okay. Well, we need to distribute from both sides, so let's distribute the delta T first. So we still have our delta x equals 1/2 times. Distribute the delta T gives us 2VI delta T plus A delta T times delta T, so plus A delta T squared. Delta T squared. Okay. Close parentheses. Now we have to distribute the 1/2. So we're going to finally end up with, I don't know why I wrote an A, delta x equals, well, 1/2 of 2 cancels, so VI delta T plus 1/2 A delta T, and that delta T is squared. And this is our formula that we're going to want to use. Notice how this formula gave us VF, VI, A, and T. This one gave us delta x, VF, VI, and delta T. This one leaves out VF, and we have the other 4. Okay, so let's do a couple quick examples. Here we go. Here's another example. Maybe hit pause and see if you can do this before you get help from me. You know, if you're not feeling brave, then just watch me do it, I guess. But maybe a good experience for you to try it and then see where you get stuck, or if you can do it. If you can do it, that's great. So, going once, going twice, I'm going to start. It says a plane starting at rest at one end of a runway undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed at takeoff? How long must the runway be for the plane to be able to take off? Alright, well, let's start by listing our knowns and our unknowns. It says a plane starting at rest. Starting at rest. This is one of those things that students always screw up. Starting at rest means initial velocity is 0 meters per second. As it running at one end of a runway, goes uniform acceleration. Okay. It gave us the acceleration. So the acceleration is 4.8 meters per second squared. And it gave us the change in time. It gave us delta t, 15 seconds. Then it asks, what's the speed at takeoff? Well, at takeoff is the end of the runway. That's when you're done with the runway. So it's not a delta. That's just final velocity. And we want to find it. It also says, how long must the runway be? Well, that's our displacement. And we have to find it too. So we have to find both of those different variables. So let's find speed at takeoff first. So that's final velocity. Let's find that. So we're looking for final velocity. We know initial velocity, we know acceleration, and we know time. Do we have an equation that includes those 4 things? Well, we'd have to check our notes if we just don't know them all off the top of our head yet. And as it turns out, we do. We have an equation that has exactly those things. We have an equation that says VF equals VI plus A delta T. All of our units agree here, so we can plug straight in. We can say VF equals VI, which we had, 0, great, plus A, which is 4.8, and then I should leave my units, meters per second squared, times delta T, which is 15 seconds. Alright, so VF is going to equal 4.8 times 15 is 72. Meters per second times seconds, that's seconds over 1, so the seconds cancels one of those seconds, so we end up with meters per second, which is what we expect a velocity to be, so we can write this down. We now know the final velocity, 72 meters per second, which is pretty quick. A meter's pretty far. So 72 meters in a second, that's not slow. Alright, so what do we need to do next? Well, we need to find the change in displacement. We need to find the distance traveled, or the displacement, however we want to say it. Change in x. Well, we've got initial velocity, we've got final velocity, we've got acceleration, we've got time. So we can do whatever we want, really. Let's use the one that says this. Let's use delta x equals vi delta t plus 1/2 a delta t squared. And we just plug in, because we're already solved for delta x. So plugging in, delta x equals vi, which is 0. That's nice, times delta t times 15. Why is that nice? Because that's just going to cancel out, but we'll continue. Equals 1/2 times the acceleration, which is 4.8 meters per second squared. I should have written the units here, but I didn't because I knew it was going to cancel. Times the time squared. The time is 15 seconds, and we're going to square that. So we know that cancels. 0 times 15 is 0. So delta x is going to equal 1/2 times 4.8 times 15 squared. Okay? Doing the arithmetic there, we're going to end up with 540. Now, we ought to get meters because this is a distance. Let's see if that's what we do get. We've got meters per second, and we've got seconds, but those seconds are squared. No, actually, meters per second squared. Excuse me. Well, yeah, that works out. The second squared cancels. We're left with just meters. That's what we wanted the answer to be, meters. So we know how long the runway had to be, 540 meters. This question had 2 parts. Wasn't that bad. Now, we didn't have to rearrange any equations here, but that's just algebra. And if you need help with that, please get it. But really, you should be pretty good at just rearranging algebraic expressions by now. You're seniors. This shouldn't be a big deal for you. Alright, so what if they give us a problem that neither gives us nor asks for time? We don't have an equation that can handle that yet. We would need an equation that had VF, VI, A, and T. Or excuse me, A and D, or X, excuse me. VF, VI, A, and X. So let's make an equation that does this. So we can do that, because we're awesome. So let's start with this one. Start with delta x equals 1/2 times VF plus VI times delta t. Okay. Order actually doesn't matter here. Let's solve this for t. So let's multiply both sides by 2. So we can get 2x equals VF plus VI t, delta t, excuse me. Let's divide both sides by that sum, divided by VF plus VI. I'm actually going to switch the order for this next step, just to be consistent with what the book does. So we end up with delta t equals 2 delta x. My delta went away. Keep dropping my deltas, I apologize. VI plus VF. And I just switched the order because that's what your book does. And I want the equation we end up with here to look like the one from your book. Okay, so we've got that. What good does that do us? Well, we can take that and plug into this equation. VF equals VI plus A delta t. And we can plug this into delta t. So let's do that. So I have Vf equals Vi plus A times 2 delta x over Vi plus Vf. Put parentheses. So we get Vf equals Vi plus 2A delta x over Vi plus Vf. Okay, this is where the algebra gets kind of silly. Subtract Vi from both sides. It cancels, so we get Vf minus Vi equals 2A delta x over Vi plus Vf. Okay, I'm going to clean this up. Okay, so here we are. We've got this formula. Let's multiply both sides of this equation by Vi plus Vf. And then multiply this side also by Vi plus Vf. Okay, this Vi plus Vf will cancel, because that's division, multiplication. It's going to cancel out. So we'll end up with Vf minus Vi times Vi plus Vf equals 2A delta x. If we do the FOIL method to this, we get Vf Vi first, outside, plus Vf squared, inside, minus Vi squared, and then last, minus Vf Vi equals 2A delta x. Well, Vf Vi and minus Vf Vi cancel, so we have Vf squared minus Vi squared equals 2A delta x. And if we add Vi to both sides, I'm not going to write this out, but if we add Vi to both sides, we can end up with Vf squared equals 2A, well, it's usually written this way, Vi squared plus 2A delta x. And here's our fourth and final formula for today. He alliterated. Vf squared equals Vi squared plus 2A delta x. And this formula doesn't include time, which is what we wanted. We wanted a formula that didn't include time. So now we have 4 different formulas, and each one doesn't include one of the 4 constants or variables. We have one that leaves out acceleration, one that leaves out distance, one that leaves out time, one that leaves out initial, one that leaves out final. So we should be in pretty good shape. So let's do an example. Okay, here's our last example, I think. It says a person pushing a stroller starts from rest, uniformly accelerating at a rate of 0.5 meters per second squared. What's the velocity of the stroller after it's traveled 4.75 meters? Alright, let's write down our knowns and unknowns. We're starting from rest, so remember that always means Vi equals 0 meters per second. And we like it when that happens because it makes our calculation easier. Uniformly accelerating at a rate of 0.5 meters per second squared, so we've got acceleration, 0.500 meters per second squared. What's the velocity of the stroller after it's traveled? So that means Vf is our unknown. That's what we want to find. And it has traveled 4.75 meters, so the change in x is 4.75 meters. Well, we're going to get to use our formula we just came up with. Vf squared equals Vi squared plus 2A delta x. So we can plug in, because all of our units agree. We've got meters and seconds and meters per second squared. No kilometers or minutes or anything like that. So Vf squared is going to equal Vi squared, which is 0 meters per second squared. And that's just going to drop out, plus
2 times A, which A is 0.500 meters per second squared, times delta X, which is 4.75 meters. Okay, so simplifying this, VF squared equals 0 squared 0, so that can drop out. 2 times 0.5 times 4.75. 2 times 0.5 times 4.75. I can't do that in my head, so let's see. 2 times 0.5 times, oops. Yes, I can do that in my head. What am I talking about? Half of 2 is 1 times 4.75 is 4.75. Great. Okay, so meters per second squared times meters, so that's meters squared per second squared. Well, that's weird, because that's supposed to be a velocity, except that we didn't finish. This is velocity squared, final velocity squared, so we got to take the square root of both sides. So that's going to cancel the squared, so we get VF equals, when we take the square root here, we get down to meters per second like we expect. Square root of 4.75, so I have that already. Square root of 4.75 is about 2.18 meters per second. So our final velocity is about 2.18 meters per second. It's not that hard. I hope you can see the benefit of writing down your knowns and unknowns. I only did one where we had to rearrange, and I'm wondering if that was a mistake. But really, the algebra shouldn't be that bad for you. So please rearrange before you start plugging in, because if you start asking for help and I ask to see your work and you have it rearranged first, I'm going to tell you to go rearrange first and try it again. And that's not being mean, that's just, you really make far fewer mistakes when you do it that way. We're going to have mixed problems. The hardest thing you're going to have at first is picking which equation to use, which is why you write down your knowns and your unknowns like I've been doing here. I've been trying to model that for you so you'll do it correctly when the time comes. Because if you write down your knowns and your unknowns, you should be able to find the right equation by looking at what you have and what the different equations show. So you should have 4 equations new today. This has been chapter 2. This section started on page 48. So if you flip through the book starting at about page 48, you'll find all the equations again if you need them. Of course, you can just skip back in the video. So best of luck. Get lots of help. Help each other. Be a friend.